In 1991, a collaborative team led by Professor James Fujimoto at MIT published a paper in Science introducing a fundamentally new type of imaging modality, optical coherence tomography, or OCT. OCT provides real-time three-dimensional information on the structure of the eye, aiding in the diagnosis of disease, assessment of its progression, and response to treatment. Since its development, this technology has had a worldwide impact on healthcare, extending beyond ophthalmology to other medical specialties. The history of OCT highlights the importance of environment, education, and collaboration among diverse teams of people.
I came from a middle-class family. We lived in a working-class neighborhood in Chicago. My parents were Japanese Americans who grew up in California, but because of World War II, they couldn't go to college, although they wanted to. That had a big impact on our lives. In my early teens, I built a television from a kit and thought about a career in television repair. However, my life was profoundly changed by a family friend, Tom Tanabe, who played bridge with my father. Tom was one of the few people my parents knew who had gone to college and understood the implications of a good university. My father wanted me to attend a local Chicago college, but Tom told him MIT was the only engineering school that everybody recognized. He said, "But of course, you can't afford to send him there." My father was so upset that he vowed to send me to MIT if I was accepted. I've been fortunate to work with outstanding colleagues and students and to have the support of family and friends throughout the years. But it was the influence of my parents and of Tom Tanabe, who challenged my father to send me to MIT, that is the reason I am here today. I am forever grateful to have had mentors with great insight into art and science at an early stage in my life.
At MIT, Fujimoto was fortunate to study for his doctorate with Professor Eric Ippen, who pioneered the field of ultra-fast science. Ippen had a profound impact on Fujimoto's scientific training and became a mentor throughout much of Fujimoto's career. Fujimoto's early research focused on femtosecond measurements of ultra-fast phenomena in condensed matter physics. He began biomedical research by chance when Dr. Carmen Pugliafito, a retinal specialist at Harvard Medical School, suggested exploring ultra-fast lasers for eye surgery. Fujimoto realized that it's possible to do femtosecond laser measurements in the eye. This is what led to the concept of using echoes of light similar to the way that you would use ultrasound. The group showed it was possible to measure corneal thickness and internal structure of skin. However, the detection sensitivity was limited, and femtosecond lasers were large and expensive. The solution was interferometry and methods from optical communication. Eric Swanson, an expert on fiber optic communication at MIT Lincoln Laboratory, joined the collaboration.
I'm very fortunate to have met Professor Fujimoto and been invited me to get involved with this technology and all the collaborators that we've worked with over the years. So I'm just proud to be part of the development of this technology and the impact it's had on quality of life.
The research team benefited from the diverse background and different levels of experience of its members. Dr. Joel Schumann, a glaucoma specialist at Harvard Medical School, collaborated with the team to perform studies on cow and human cadaver eyes. David Huang, a Harvard-MIT MD PhD student, demonstrated that it was possible to see structure inside the retina and create cross-sectional images.
I was looking for a PhD project and I was lucky enough to end up in Professor Jim Fujimoto's femtosecond laser labs. We first look at measuring the thickness of the cornea and the depth of the anterior chamber, and then we look at measuring the thickness of the retina. We were able to see layers inside the retina, not just measure its thickness. And so we started scanning the beam, and that was the first OCT image.
The first OCT images required large equipment and several minutes to acquire a scan. Swanson increased the speed 100-fold and designed a system that could image patients. The prototype OCT instrument was transferred to the New England Eye Center, where Carmen Pugliafito and Joel Schumann, along with Joseph Izat, a postdoctoral associate at MIT, and Michael He, a Harvard MIT MD PhD student, performed studies in over 5,000 patients. These were the first demonstrations of OCT in diabetic retinopathy, age-related macular degeneration, and glaucoma. In order to have an impact, technology must be commercialized so it is available to the clinical and scientific community. Puliafito, Swanson, and Fujimoto co-founded a startup company to translate OCT from the laboratory to the clinic. The company was acquired by Humphrey Zeiss, whose president, John Moore, was a visionary and accepted the tremendous cost and risk of developing OCT for ophthalmology. Although OCT could generate retinal images at resolutions which were previously impossible, there was no precedent for using this in diagnosis or treatment. Dr. Jay Wei was the lead engineer who developed the first OCT instruments at Zeiss in 1996. Wei later founded the company OptoView, which developed advanced spectral domain OCT and OCT angiography, a powerful method for visualizing retinal vasculature by detecting moving blood cells. These advances accelerated research and understanding of disease mechanisms. Although OCT was rapidly commercialized, its initial use in ophthalmology was limited. Widespread adoption of OCT was driven by Dr. Philip Rosenfeld's work on antivascular endothelial growth factor for exudative age-related macular degeneration, or AMD. OCT can detect retinal fluid exudate and determine the need for retreatment. OCT personalized treatment has saved billions of dollars in healthcare costs. In the future, OCT and retinal imaging will be performed robotically in drugstores and primary care physicians' offices. Combined with AI, this has the potential to not only detect vision-impairing eye disease, but also diabetes, risk for heart attacks or stroke, as well as neurological disease. OCT is being developed in many other clinical specialties. Intravascular OCT is the largest clinical application after ophthalmology. Cardiologist Mark Brzezinski, MD, PhD at Harvard Medical School, proposed developing intravascular OCT and joined the collaborative team in the mid-1990s. Brzezinski led the first OCT studies on vulnerable plaque as well as on many other applications. Intravascular OCT was commercialized by a startup company co-founded by Swanson, Brzezinski, and Fujimoto in a joint venture with Zeiss. Intravascular OCT can guide treatment for myocardial infarction and improve outcomes by reducing rates of major adverse cardiac events. The development of OCT required multidisciplinary collaboration among investigators from diverse backgrounds, with experience in science, engineering, medicine, and industry. The history of OCT shows us that it is possible to make powerful contributions at an early career stage. At the same time, it also underscores the importance of experience and persistence.
I don't think there is a profound shortcut to success. It's a combination of many things. To be successful, people need to adapt to the situation around them. Sometimes that requires you to become a different person. That is, to continuously grow and try new approaches. In any collaboration, everybody comes with a different perspective. There's always a range of people with different skills and expertise, with strengths and weaknesses in different areas, and with different personalities. We're surrounded by extremely intelligent and talented people. You should emulate the best characteristics and methods of each person around you. The other component to success is hard work. You must be interested enough in what you're doing to take the time to refine your skills and technique. It's like practicing music. You can't do something at a creative level without commitment, either in the arts or in science. A career in science can be tremendously rewarding, and you will have great opportunities, but you must have a strong commitment to strive for excellence.
The history and evolution of OCT is only one example of the translation of new technologies and methods to clinical care. Technology is rapidly advancing, and its increased role in medicine promises to have a powerful impact on health and quality of life.